you do not apply the same method you apply for homogeneous sample, okay? And then what we do in the case of clay materials, what we can do when we have turbostratic disorder, and some little bit example on the amorphous material that we saw in the previous lecture, actually. And then some development, okay, for trying to what we do when we have big problem. And the two big problems we saw before are texture, and that one we actually can do something, but the big one, as Jan pointed out before, is really the microabsorption. So we will see as this is actually the biggest problem for quantitative phase analysis. So I like to use actually just this formula that is actually the formula we normally use for computing a powder pattern, okay? The usual one, use it in the Rietveld. So actually, we saw from day 3 to 6, we saw crystal structure. So everything concerned to the structure factor there. And actually, yesterday we saw all the crystalline size defect, planar defect, etc., going into the line broadening there in the profile shape. Today is the day we see a phase quantity that enter the volume fraction F over there, or weight fraction as in the Jan equation you saw in the first lecture. The absorption term is over there, and so we will see something, okay, in this lecture, especially it enter both the microabsorption problem and film, okay? We have also texture, and tomorrow you will see texture entering the pK, that is the texture factor, okay? So, or you call it preferred orientation, as you like. You will see also something in my lecture, as I work too much on texture, so I cannot decouple my example from texture. And then also tomorrow you will see residual strain, so something that goes in the peak position. With the set parameter. Nothing on the background. Yeah, that's only Jan, only Anne pointing out you want a flat background. Yeah, if you deal with the amorphous, you want a very flat background, as lower as possible. Okay, so actually, this is, well, actually I put one layer red, another green, and turned out could be the Italian flag, so I keep it. So normally, we have a multi-layered model. Below there is also the subset, okay? And so actually what is happening, we have an incident beam, the outgoing beam, and actually the absorption, we need to treat it per layer, okay? So there is this, okay, nice formula I actually now I'm just using this one in my program, as it's very nice because you don't deal with any tilting, clarify, etc. You just only need to put the incoming, the inclination of the incoming beam and outgoing beam, okay? And then there you have the absorption for the phase P in the layer J. Okay, and this one easily computable if you have the composition of the phase. So actually, first problem. Suppose you have a layered material and you analyze with the Rietveld, but you don't put, you treat it as an homogeneous sample, okay? What is happening, actually? So at low angle, you have an incoming beam, outer beam. The volume diffracting will be mainly concentrated in the top layers, okay? And what is happening then, the reflection for the top layer at low angle will be stronger. Instead, for the bottom layer will be very weak, unusually weak, okay? And then you go at high angle, okay? And it's happening exactly the reverse. So the top layer become weaker respect to what they are at low angle. And instead, the bottom layer become stronger respect to the low angle part. So actually, what is happening in the Rietveld, it doesn't know you have a layer structure. what you get the B factor for the phases that are more on top. You get B factor that are much bigger than 0, and B factor lower than 0 for the phases concentrated in the lower layer. So this is one example, so what we can do. So that was a Inconel 738. Well, this is at the beginning of the 90s, so this old, it was with one of my old program, okay? We have, this was oxidized at high temperature, so we have several oxide. We are interested in locating where are the oxide. Normally, for example, the corundum, the aluminum, just grow inside the substrate, the matrix, okay? And for example, other oxide, like chromium oxide or titanium, grow outside, so we go on top. And then there is the kinetic, who grow first and later. So if you treat it as an homogeneous sample, you get this one, you get some volume fraction that don't mean nothing, okay? Because, for example, you get the nickel-based alloy that is 8.6%, but is in reality your big sample, okay? And in fact, this kind of sample is better to treat it in thickness of the layer. Then you are more interested in the thickness of the layer than volume fraction that are meaningful. And you look at the B factor, okay? So you see, in fact, the matrix, the B factor goes, that is down, the B factor becomes negative quite a lot, and the top layer, so what probably goes on top, get a very high B factor. So we now, so what we can do, we model, so we model. We put a model with, we put one layer for each composition. We start saying, okay, we put on top the one that has the bigger B factor, and all the other in sequence. Actually, we don't want to put the aluminum oxide on top, even if the B factor is, we don't trust too much. But in any case, you do another Rietveld analysis, and you analyze again your B factor. Okay, in the analysis you do now, you fit the thickness instead of fitting the volume fraction, okay? Then you analyze again the B factor. If one phase has a B factor that is bigger than 0, you have to put that layer over. If one gets negative, you have to put that layer below. And you sort out that way until, okay, in this case, actually some of the oxide mixed in the same layer, so, and some of them split in 2 layers. So the final, okay, well, I didn't have so much time. Every time you run one of these, at the beginning of the night, it was half a day of computation, so you cannot do infinite number of trials. But at the end, you see, I didn't work out too much the chromium niobium there, okay, and the chromium and alumina. But the other, when I tried to mix in different layers, I could get a good B factor. Then at the end, so you can refine also 2, 3 different phases in the same layer, and you fit the thickness. You see there is the big thickness is the layer number 2, where there is the chromium oxide and titanium oxide. Remember this, because we have done then the EDAX map to see where the elements are. The niobium, in fact, is on top. Okay, you see the element. There is a little bit of tantalum that is just substituting the niobium. You get the chromium in the big layer, in the 2.2 micron, okay, in fact, and the titanium also is distributed in the same layer. So this was done after I finished the modeling. So I didn't know it. We just tried to make it to see if our model was really the correct one. So we managed to get one of these EDAX map SEM. The aluminum, in fact, the aluminum was a big problem. Also, the map, say, is down. It grow inside the matrix, but it always come up with a big B factor. Okay, then the nickel, and so on. So, next example, now we go quickly to the when we have clay material, okay? That was when I was in 2009 in Berkeley again, and they always get out with some problems, so they are, in Berkeley they have this clay material, they want to study how they deform in pressure to simulate what is happening in the crust, earth crust. So they have 2 samples, different pressure for different days. They wanted to check the texture at the end resulting. So there are also some parameters interested for the people. So you have the cylinder was in compression, then we cut some slab. The slab, 3 millimeter, were cut parallel to the compression, okay? Because then we put this one, so we put in transmission, and if we cut that way, we have the fiber texture that is just going in the plane of your image plate. So you can see better some ring. If you put the other way, so if you cut perpendicular to the compressing axis, then it is a little bit more difficult to see the texture part. So you rely only on changing between intensity instead of changing of the intensity along the ring, okay? Then here, then we sample our, okay, image. Yeah, we use MAUD, we import the image, sample out, okay? And then we use, for the microstructure, that is the big problem, is actually we use anisotropic crystalline size microstrain and the single layer model of UFER. Yeah, that was already mentioned by, I think, Arne Kent mentioned it first. Then using the texture, that was our goal, to get the texture. EVINF is the one we use always at the beginning, that is giving out where the main component was. We saw there was only one fiber component, so we model it then later with the standard function that give us a much better result. Okay? There were 3 phases, oh, actually 4. I forgot the Crystallite, so we had to quantify also them. So what, if you start, you put the ideal structure, okay, and you just use only anisotropic broadening, then you don't get a very good fitting. Texture turned out very weak. We were not what you expect for a clay that is also in compression. So we decided to have a look on this UFER model. At the beginning, we imported it, just the structure factor computed from BGMN in MAUD. Then we needed to refine, in reality, the structure, so I incorporated it in MAUD. So the model is very simple. So if you look in the reciprocal space, when you have a turbostratic disorder, suppose along the C-axis, you get a long rod, okay, where you have reflection that are not 0,0L, and you get the spot on the 0,0L, anisotropy for the broadening, okay? So what is the idea of UFER? You construct a supercell, you fill up only one layer, so one cell on the bottom or the top, whatever. So you get something like this one. If you take a longer, so a bigger supercell, you put much more dot in there, and you simulate much better a long rod. The problem, you get also along the 0,0L, you get a rod, so you do a mixed layer in which what you do, you just compute the 0,0L intensity based on the not supercell model, so the original model, and you compute only the other peak using the supercell. And then you have to scale the two due to the fact that you are using a supercell in one direction, but that is easy. Okay? Then you have also to add some additional broadening, because the broadening along the 00L is much different normally than the other one. Okay? So here is when you put, you start from the hidden model, you put the Ufer single layer model, you generate a lot of reflection from the supercell, and it's quite nice as you can, okay, where has gone my, oh, here it is. Okay, so you see here, you go down, and also here with the asymmetric part typical of this kind of material, but the 00L is not affected, right? Okay, then we refine, okay, the structure. We just put the octahedra, tetrahedra as a fragment. We refine the occupation of the, this was calcium, right? Morillonite, calcium, aluminum where it was, okay? And it was quite easy because you can model exactly with the, so we refine the structure and you get a very good one. Okay, I will talk later. Also the Opal-CT actually was faulted, okay? So we needed to use the model also for the Opal-CT to get it correct. So did the texture turn out okay? Well, actually what you see here is just, normally we work with 72 patterns. We actually divided our image in 72 patterns. We fit all the 72 patterns together with the texture. What you see here is just the final summation in the plot, okay, of all patterns, both the data and the fitting, okay? So when you want to see also what is changing with the pattern number, or here you just look at the azimuth angle around the, then you see, well, mainly on the 00L peak, the calculated and measuring intensity, but also over here. Actually, I normally prefer to see it in plane, so here there are the experimental pattern, and here is the calculated one. This is also the background is changing a little with the image. So this was sample 1. This is sample 2. He has the variation of the intensity is a little bit stronger. So we get nice ball figure. Well, tomorrow Bob will talk about what they are. Only here we are interested just to compare on the maximum intensity for the texture here, the sharpness. So here you see the sample 2 has nearly 30% more texture than the other one. Okay, yeah, and okay, just saying here is the texture we get if we don't use the single layer model. So if we don't model correctly the microstructure, and here is using it. And you see that actually the texture is a little bit, okay, it's not a strong texture here. Actually, this is 1.3, so it's 30%, but you get half of it if you don't use the correct model. Okay, crystallite size and microstrain, different direction, just to show how they differ. Opal-CT was another story, and actually this one also is a faulted structure in which you have a difference taking, okay, similar to what you get in FCC HCP. And it can be modeled by the ideal tridymite at high temperature, a crystallite. This was proposed by Guthrie, Bish, and others in '95. So they use a Crystallite for modeling it, okay? And, but using the single layer model, you can do the same. So you take the hexagonal, so you put an hexagonal tridymite, and you just model a turbostratic disorder. And actually, so we then try to see if our model was really, so looks this to peak is similar this to peak of, well, they had much more broadening due to the fact they were having smaller crystallites, so 2 peak and the third one, and here is the third one, so we get the same intensity. Actually, this is, I leave this one, as you see this oscillation, these are coming from the single layer model and depend on how much you choose for the supercell. Here, for example, if I take 10 times the cell, then you see some oscillation, depending on how small are the crystalline or bigger. If you want to avoid the oscillation, you just take a bigger cell so you approximate better, okay? But it takes longer time. So normally, depending on how big or small are your crystalline, you choose a supercell that you just smooth out the oscillation that are due to the fact we are using small sphere to model a rod, okay? Okay, well, we can get the quantitative phase analysis. Quartz was very small, so 0.2%, 0.3, while we have a huge amount of data from one of these images. So we are very sensible to the quantities here. And there was a little bit of crystallite, the Opal-CT. We also get the water occupancy, etc. So let's go further. Oh, this I just insert this morning. Yeah, I was remember yesterday Andrew mentioned about turbostratic disorder in carbon. Okay, so this is a carbon-carbon composite. Carbon-carbon brake disc for competition. Yeah, I have a friend who works in one of these factories. Sent me, he has this data he wanted to characterize. So I tried to bargain the analysis for a couple of these discs for my motorcycle, but didn't succeed. And so I didn't send him only the picture. Yeah, and so you model here. He was surprised because he didn't tell me there were two carbon phases, but I could guess because normally carbon-carbon have two phases in it. One is the more layered one, the matrix, and the other are short fiber. So here we model also the difference between the two. You see the green and the blue. They are different. Okay, use this single layer model, same model for both, but here the difference between the two is also the crystallite part, because one is elongated along one axis, so the fiber direction, the other are elongated along the plane. And you get very different, and you can model quite well. So you can do quantitative analysis and that, and actually turn out very good with what he expected from that sample. So now, Anne mentioned before, okay, how to use the Rietveld with the labile approximation or the X-ray amorphous, right? So labile come out with this fact that you can use a crystal structure, you distort the Riet from the amorphous point of view, simply enlarging the peak shape. So it means you choose a very small crystalline size, microstrain, like it is a nanomaterial, okay? So it's pretty easy to use in any Rietveld, straightforward. The only thing, you need the crystal structure, so the local structure of your amorphous. So you need to model it. Labile has made a huge work to find out the one for silica glass. Turned out is Griseofulvine. Oh, I don't pronounce it in English. It's an Italian name. I don't know even how to pronounce it. But, well, it was actually turned out was the same structure predicted at the beginning of the 19th century, so that, or the 20th century, sorry. Yeah. So here is how it looks in the real space in our powder diffraction. So our idea was, okay, if this can model pretty well so you can model with the nano approximation an amorphous. Well, and the local structure, the short range order is approximately the same, well, is quite the same. So you get the electron density correct, mainly. For quantitative analysis, when you have the correct electron density, you are pretty done, okay? You don't need more than the correct electron density scaled correctly. And the model of labile give you that, okay? So we thought, okay, what happened? Can we use it for quantitative analysis? So we put together, so one colleague of mine mixed silica with alumina and measure it and give me only the pattern. I was just analyzing it, and at the end, we shared the result to see if I was getting the same quantity it was put in it. And it turned out it was incredibly matching. Yeah, so we say, okay, it's working. So the approximation of the die is really giving you the scale factor and everything you need for the amorphous. So we used it several times for, and also I tried it for polymers. For polymers, it turned out quite easy. So it's not so easy on inorganic because most of the time the the amorphous, the amorphous polymer, let's say, has a polymer of an inorganic substance, doesn't have the same local structure as the crystalline one. Some of them has. Well, for example, titanium oxide, the one that has the same structure as the amorphous is the brookite, not the rutile or the anatase. For polymer, instead, is I found out that nearly always when you use the crystal structure for the amorphous part is actually reproducing it very well. So, for example, in this case, without any standard, internal standard, external standard, we can get the crystallinity for example, this was polypropylene, okay? Then we used it also for the pharmaceutical field, in which there were these people that by ball milling were just disordering, so amorphizing the incipient inside the carrier, okay? The carrier was most of the time PVP, polymer. So we take the incipient here, the Nifedipine, check the structure, okay, just to be sure we had the correct structure. Here is our PVP, only the polymer. Actually, in this case, when we use let's say the X-ray amorphous from the crystal structure of PVP, it doesn't turn out very well. So here we will see later, we want to characterize two amorphous, okay? So we need to get the best we can, so we decided, okay, we don't care about the structure, so we use the Ponck's way, okay? And actually, instead of just fitting some experimental structure factor, like labile, I prefer to extract an electron map and use that one, just so I'm more sure I can compute every peak or outside or whatever. But it's simply the same. So I could get, you see, a very good fit using a map sufficiently big to fit this one. Now, first thing, what you do next, as explained by Anne, you prepare your calibration sample. So you put together, I think here we put together 50% of Nifedipine, 50% of PVP mixed, and you calibrate the factor, the scale factor, okay? In MAO there is a phase scale factor you calibrate, then you fix for the other analysis. So we have our PVP scaled for the quantitative analysis, and then here you see 0 minutes, so the beginning, then milling, 10 minutes, 30 minutes, 60 minutes, and so on. You go to the quantitative analysis. In this case, the Nifedipine doesn't really amorphize too much, only not more than, you see, between 15 and 20%. The error, you see, is quite big. In reality, when you go with two amorphous, the error is not very small, in reality. Okay. And then, okay, we could characterize also the microstructure part, seeing that, okay, the crystallite side don't decrease over a certain level just because you lose the nano size that is amorphizing, so you only reach a certain level and you just decrease only the biggest one. And the same happening for the microstrain, that doesn't change too much, really. You see the scale is nearly there. Griseofulvine, another incipient, or just to show I have a nice image plate. Well, now it's old, I'm replacing it. Well, I can collect in one shot. This is curved, so, and then I use it for texture normally, or when I wanted very big intensity. So this is in less than 30 minutes or 1 hour, you get a very nice intensity. We fit with our Griseofulvine, just to be sure. Okay, here, if you want to see in 2D, yeah, we use as much data as we can. And okay, just to check the Griseofulvine-amorphous, okay, when we compute is different from the PVP. And actually it's not a big difference, so we have to rely on the difference of these two amorphous for our analysis. So, well, here are several patterns for different milling time, and here is the analysis. So well, this was prepared by my PhD student. Yeah, he didn't put any error, but you see here the error is in any case big. When you want to, we are really on the limit on this one. This one is good. The Griseofulvine amorphizes quite easily inside the PVP. Okay, so we have, okay, what happens if you have preferred orientation? Okay, if you can, my way, okay, you try to re-prepare your sample, avoid them. Sometimes you cannot avoid them, okay? So my way to do is to have a machine that collects several patterns, different inclinations, so I can use a Rietveld texture analysis and get corrected for the. But if you are working with one pattern, then you are a little bit, you have to rely on that one. So this was a laminated sample. Well, we measured, I took this one to do this example just because on this one, we measure the texture, and it's not a fiber one. You see it's a lamination texture. We measure several to get the texture by Rietveld. And at the end, for the next example, I will take just only this, the pattern collected in the center of the pole figure, okay? That is exactly the pattern you get when you collect in Bragg-Brentano. You are only collecting for every reflection the center of every pole figure. So you don't have all the information from the other point. So here is just the pattern you want to see. And then I made, so I start from that one, assuming, okay, I want to do a quantitative phase analysis only with that one and see, applying all the method to see what is happening. And also I divided in two ranges, using full range, so very big, or a reducer range from 0.79 to 2.2, okay? So if I can correct with the ODF, the true ODF, I should get 66.7%, okay, to get the correct one. And so you are near there, okay, with one pattern, okay, if you can correct for the true ODF. Let's now say, okay, I don't put any correction, so I use a random texture, okay? The RW is very high, 31, okay? And you see 35, but it's not bad. The analysis is 65 and 63. If I put the match Dollase, then I get better RW, okay? But the quantitative phase analysis get worse. So, in fact, in the past, people were saying always, if you are working for quantitative phase analysis, get a worse fit, but don't use any preferred orientation correction. And use as many peaks as you can, so with the Rietveld. So then, now there is also this harmonic, wonderful, you just push the harmonic, you can fit everything, okay? So, but actually, so if you use L, the expansion to 4, 27. Yeah, going to 6, you get half of the RW, but the phase quantity is worsening, okay? And even worse when you get to 8. So you improve the fitting, but not the analysis. Actually, with the small range, it turned out at least one good one here, the 6, but just because you see the trend is to increase the copper percentage, and it started from a lower value, so it passed through a correct one. So then, okay, you see, if normally with the texture, okay, better in any case, if you don't know what you have inside, to not use any correction. At least you have less probability to get a false result. Probability, okay? Maybe you get a better result, but microabsorption, so this was a slide prepared by Jan Massen. So the problem is when you have big grain of one phase with high absorption and the other phase has a low absorption, so the beam is stopped more by the high absorbing grain, but less by the other one. So turn out you see less the phase with high absorption and more the phase with low absorption. So actually, for example, Brindley put this correction equation, very simple, okay, in which you have to know the shape of your particle and the dimension. If you don't know that, the equation doesn't work very well. So we used it, this aluminum nickel particle phase, okay? Here is a big table. So let's see, here, no correction, okay? So we know, here we prepare the powder at the beginning, not the composite, just to check, because we wanted to. And so you see, you put 10% of nickel and you get 5%. And nearly, yeah, 20 is 12, 30 is 20, okay? So then you apply the cubic correction. So suppose your particles are cube-like, okay? And you get a nice correction. And then, well, but because we know the particle size from the SEM image, okay? Yeah, if you don't know that, you get a little bit worse, okay? But then if you apply the spherical one, from the CM image it's not clear if you have a spherical or cubic particle. Actually, it's not so good. So the Brindley correction, actually, it may work, but if you guess what you have really inside. So actually, microabsorption is a big problem, so maybe you want to use another technique to avoid it, if you really need. And actually, remember, was Shankland, first day mentioning this wonderful piezoelectric vibrating sample. It was you? Yeah. It's wonderful. I actually use analyze. I went to in situ, they wanted to use mouth for the quantitative analysis of the, but actually, so you don't get any texture, perfect statistics, but let's say no quantitative analysis you can do on it. And actually, after I explain them, I think they don't push anymore the quantitative analysis. The problem, can you see which problem you have? So here you have this one. You have this particle moving, and then you have a small beam normally that the particles, okay, and then diffracting. It's very good for statistics and texture because the particle may arrive in any orientation, and after a while you get a random sample. But it's not. The problem is absorption. Yeah, you are eating one particle at a time. So you have a problem with the absorption. To correct it, you need to know the particle, dimension, and shape. You have not a particle inside the matrix, so you don't have anymore the mu, the Mach factor of Jan mentioning, okay? So you have single phases. There is no way to correct it unless you know the mean size and mean shape of your particle. That's the problem, yeah. Okay, I think I have finished. Well, actually, let's see. This was where I wanted to arrive. Now I only put down, yeah. Yeah, the only, play. This one, what next? Well, I will show tomorrow. I have a new one for automatic search match and quantitative phase analysis, something I had to do in the last year and turned out wonderful. So without user intervention, so from the search match to, and also I'm working now, well, if you use MAUD, you have seen maybe in the last, there is an XRF model. And last is, okay, the MAUD workshop, but also for the other one, Jesus and Topaz, we actually decide, okay, in principle, you can download the program and workshop file from Eris's server, but I wasn't able up to now to upload them. Yeah, I asked if the organizer can help me, but because I have more than 350 megabyte, and it always stops. There are too many connections on. So the other is, we decided, okay, unless we change, but we divide in two sessions. So Topaz will be probably in San Francisco with Jan Madsen, so tomorrow. And instead, with MAUD and Jesus, we divide by time, so we will do first MAUD and then Jesus, as we prefer to use the big screen, okay? So in the approximately, okay, will be 1640 to 18, or if we finish before, we may have a break also in between. Okay, so that's.
Thank you, Luca, for this very nice overview. Are there any questions? Yes.
Olienko, Rigaco, Berlin. Luca, I have a question concerning multi-layered samples and grazing incidence angles. The surface roughness and maybe even interface roughness shouldn't be included in consideration because of it changes at least absorption, but also maybe microstrains, gradients.
So for a grazing incident?
Sorry?
You are meant for grazing incident, right?
Yeah, of course.
Yeah. I use MAUD with grazing incident. We use, and actually, okay, I was some slide at the end for thin film, very thin film, which we use MAUD for grazing incident, reflectivity, all this stuff. Yeah, because we include all the absorption, correction, etc. It's only I didn't manage in time. I know my target was to arrive there. If I was quicker, then but I skip the thin film part. But we use it normally. Yeah, actually, MAUD was developed a lot inside an European project in which we work on such subject. Yeah.
Any more questions? If there are no more questions, let's thank again today's speakers.